Hi everyone, I'm Luis Rivera, and as you can see, my main area of interest in physics is condensed matter, and in particular, the electronic structure and properties of quantum materials. Today, I'm going to talk to you about the electronic structure of the calcium nitride and the uniaxial pressure. Next, please. The calcium nitride is a quasi two-dimensional electride which there exists excess of electrons in the layers. Electrodes have an excess of electrons in the interstitial areas of the crystalline lattice. This excess of electrons act as anions, like the chlorine in the sodium chloride. So we can name this excess of electrons as anionic electrons. There are several classes of electrodes which can be classified according to the degree of localization of the anionic electrons. The zero-dimensional electrodes have a highest level of localization of the anionic electrons. Meanwhile, the two-dimensional electrodes have a greater degree of delocalization of these anionic electrons. Next, please. Within the domain of the two-dimensional electrodes, today we find several families, as you can see in the table. All of these compounds have a structure. All of these compounds are two-dimensional electrodes because they satisfy two criteria. First, they have a layer structure, and second, they contain anionic electron between the layers. In the table, we have several two-dimensional electrodes for which calculation of the properties were conducted using density functional theory and have been synthesized. So, why study Dicalcium Nitride? Well, Dicalcium Nitride is the first electrolyte synthesized under natural conditions, and is a structure made that is easily exfoliated, and it made a good candidate for application in nanotechnology, solid-state dopants, and battery materials. Next, please. In 2013, first principle calculation was conducted to obtain the band structure, showed 3 bands crossing the Fermi level, and this means that the material have a conduction in the plane parallel to the layers. Later, experimental transport measurements on both polycrystalline and single crystal samples show that the material have metallic form and high electrical mobility. 3 years later, experimental measurements of the Fermi surface showed a closed orbit, which is typical of conductive materials. Next, please. Later, 3 studies submitted the compound to pressure, and in the first and the second, the pressure was applied uniform to the crystal lattice. As you can see, the electronic structure of the compound varied significantly with the compression, made that the compound go through a phase transition. As you can see in the electron localization plot, the anionic electrons tend to localize. Next, please. And in the second work, the electrical conductivity was calculated, and they showed that the electrical conductivity of this material is very high, and also with the pressure, the conductivity decreased. The in-plane and out-of-plane components of the electrical conductivity of the calcium nitride under hydrostatic pressure show high anisotropy in the conduction. Next, please. So in the later study, submitted a bilayer of the calcium nitride with uniaxial compression and stretching. The compression was up to 4%, and they showed that the band structure, in some regions of the band structure, the variation is minimal. For example, in the conduction bands, the variation is more remarkable compared with the valence bands. In the total charge density, we can see that with the compression, the electronic, the charge density between the layers tend to raise to it. Next, please. So, given this context, a question arises: how the electronic structure and electrical conductivity of the calcium nitride changes under uniaxial pressure applied perpendicular to its layers? We hypothesize that with the pressure, the electrical conductivity of the calcium nitride will be decreased. Next, please. The methodology involves DFT calculations using gradient generalized approximation and PVE for the exchange and correlation potential, and the quantum espresso code was used to calculate the density of states, the electron charge density, the electron localization function, the electronic band structure, and the Fermi surface. Also, the Borsuk-2 code was used to calculate the electrical conductivity. The compression in this work was up to 10%. Next, please. So, as a result, we have the ground state of the calcium nitride. As you can see, the band structure is in a dual rhythm with previous works, and we have three bands crossing the Fermi level, which is the red line, and this band is the responsible of the conduction in the material. Also, in the density of states, these bands have the highest contribution at the Fermi level in the material. We can contrast this with the local density of states, which means we say that the number of states per volume and per sun energy show. So at the Fermi level, this plot shows the local density of state at the Fermi level, and as you can see, in between the layers, we have a greater contribution to the density of states, which is down to these three bands. And we plot the electron localization function, which indicates how two paired electrons are close with different spins. And it's range from 0 to 1, where 1 means that the paired electrons are high localized, and 0.5 means that we have a free electron gas. 0 means absence of electrons. So as you can see, between the layers of the compound, we have both the localized and localized anionic electrons. The localized anionic electrons are the responsible of electrical conductivity of the material. Next, please. So, what about the compression? Well, in the band structure, at the conduction bands shift to lowest to highest energy levels, energy values. In contrast, the valence bands remain within the same range of values of energy. And in the at the Fermi level, in the path gain gamma to M, we see that the reduced slope of the bands, which means that the Fermi velocity decrease. And this indicates again that the electrical conductivity of the material decrease. Next, please. So in the density of states, we can see that at the Fermi level increase. And a narrowing energy around the Fermi energy show, which means that the anionic electrons tend to localize. And this can see very well in the electron localization function maps, where for the 10% of compressions, the anionic electrons between the layers tend to localize. Again, this shows that the electrical conductivity of the material must be decreased. Next, please. The Fermi surface was calculated, and well, the Fermi surface showed the electronic properties of metals. And in this case, the Fermi surface showed a cylindrical shape, which means that the conductivity in the material is through a quasi two-dimensional space. Also, the Fermi surface showed the distribution of the Fermi velocity and in the surface. And as you can see with the compression, the Fermi surface tend to have a deformation, which means that the electrical properties of the material must be changed. And also, the Fermi velocity decrease according to the color bars in the scheme. Next, please. Finally, the electrical conductivity of the material was calculated, and as previous work showed that the in-plane electrical conductivity have a high value. Meanwhile, the out-of-plane electrical conductivity have a low value of electrical conductivity. Also, with the compression, the in-plane conductivity decrease. In contrast, the electrical conductivity out of plane or perpendicular to the layers increase. But in general, the electrical conductivity of the material decrease with the compression. Next, please. In summary, the uniaxial compression affects the Fermi velocities of the Dicalcium Nitride, increase the density of states, and localize the anionic electrons. This impacts the shape of the Fermi surface, and as a result, the electrical conductivity of the Dicalcium Nitride decreases.